I'm John Steiner, and this is Physics 2211, Lab 4, Oscillations. The purpose of this lab is to investigate a combination of forces seen in common physics calculations such as the spring force and gravity. Furthermore, we are conducting analysis on the energy of our system as it undergoes oscillations. In this lab, we use Newtonian physics to describe the motion and forces acting on our objects. Furthermore, we use the energy principle to observe the kinetic potential and total energy of our system throughout the duration of the experiment. On this slide, I've outlined the different forces that we'll be using for the simulation, as well as the position and update formula necessary for simulating the motion of the object, as well as the relevant energies and energy principle. In this lab, we are using a model which consists of only the spring force and gravitational force to simplify our calculations. This means we are ignoring all other interactions outside of the spring-earth mass system, and it also means that work surrounding is going to be 0. Here I have our tracker set up. The systems and surroundings in our experiment are the system being the mass, the spring, and the earth. The surroundings are all other objects. The initial conditions, as you can see here, are an initial position at roughly negative 0.115 and negative 0.625 for our mass on the spring. Our experiment is releasing the mass attached to the spring, which is attached to the fixed attachment point with an initial velocity of 0. The mass is then left to freely oscillate based upon the interactions we described before. Here's the experiment running as we track the position of the mass. Now let's go over the details of the coding. First, we have our initial definitions for each of the objects that are going to be in our simulation. Then we have our initial conditions, which we specify being the mass, position, and velocity of the object. We have our delta t fixed sufficiently small so that it is a good approximation for the motion of the object. Then we have our additional constants, which will help us describe the forces acting on our object. And in the simulation loop, we are constantly calculating the kinetic energy potential, spring potential, the gravitational potential, spring potential, and total energy, as well as the appropriate forces acting on the ball that we described earlier, and we update the position and velocity of the ball using the momentum and position update formulas. Then we calculate our new energies based off of the formulas for each energy. Here's the program running with our data input for reference. As you can see, the total energy in the system is remaining constant over time, although delta K, delta UG, and delta US are all varying. On these graphs, we can see the similarities and differences between our data in the experiment and the model. The difference between the data and model predictions are most probably due to the simplified model we used, which ignores interactions occurring between the systems and surroundings, such as the drag force. Outside of those ignored interactions between systems and surroundings, there could be additional errors caused by poor tracker video quality, low video quality frame rate, manual center tracking, and low simulation fidelity. For our model system, the energy principle is satisfied. This can be observed because the total energy of our system remains constant, as mentioned before, which means that the relationship between the energies is preserved appropriately as to what we would expect. Back in Tracker, if we compare our two x data points here to find the period of oscillation because they occur roughly at the same x distance, we find that the period of oscillation is roughly equal to 1.229. However, if we use these two points here and here because they have roughly the same y coordinate, we find that the period of oscillation is roughly 1.521. These are not consistent, and this is most likely because there's also motion in the third axis, the z-axis, which we have not accounted for in this model.